Welcome back. This is CS4510, L19B, and the topic is on circuit lower bounds, or the lack of circuit lower bounds. Basically, today I'm going to be able to prove every single circuit lower bound that we ever have, because there's only like 3 of them. So first off, we took efficient time and we showed that efficient computation in a uniform sense has efficient circuits, right? We proved that time of f has circuits of size f squared. You can improve this slightly, but still that stands. Let's go the other way. Let's consider all computation and then see which one of them has efficient circuits, right? So a Boolean function is a function that simply takes as input n bits and outputs 1 bit, okay? There is no input and output in the sense of a circuit, but it is a function, okay? Don't think about a circuit that computes a Boolean function. Just think about the Boolean function as the association of input to output. Pop quiz. How many n-bit Boolean functions are there?
Uncountable.
Fix n. So it'll be some finite number. Fix n.
Maybe 2 to the n.
That's, we're getting closer. That's the size of the truth table of a Boolean function, right? Suppose this function is a truth table, right? The truth table of such a function is going to be, there's going to be some string here, something like that, right? This truth table has size 2 to the n. How many truth tables are there? How many strings can go here? Yeah.
This is almost just a guess, but n to the 2n?
Close. It's just how many, I'll ask it in a different way. How many strings are there of length 2n? 2 to the n.
2 to the n.
2 to the 2 to the n. Yes. The truth table has 2 to the n possible things, 1s and 0s here. So there's 2 to the 2 to the n possible Boolean functions of n bits. A lot of Boolean functions. We want to know a circuit, just a circuit upper bound. Forget lower bounds for a second. Every Boolean function has a circuit that implements it. Maybe it's a big circuit. How big is the circuit? What size? This is a tough question. But I claim that you can implement every Boolean circuit, every Boolean function on some circuit. That's true, certainly, right? We're not going in the sense of circuit complexity or uniform complexity. I'm asking you, let's consider Boolean function complexity, which in the sense we just have these functions and we want to implement them as circuits. Given a specific function, we can program it into a circuit, such that the circuit computes the function. What is the size of such a circuit? And I'm just looking for conjecture.
N?
But there are 2 to the n possible outputs. Actually, that's not as bad of a guess as any other, to be honest. It's the one we'll prove, simply because it's easy to prove, is going to be n times 2 to the n. Every Boolean function has a circuit of n times 2 to the n. We'll talk about improvements to that after we prove it. Proof: convert the truth table into a circuit. So the truth table is going to start with 0, 0, 0, 0, 0, 0, 0, 0. Let's just do 8 for fun, okay? And give me a random binary string. Let's do 1, 0, 1, 1, 0, 1, 0, 0. That looks good. And let's say there's a 1 here in the truth table. Let's say there's a 0 there, okay? What you're gonna do is for each row of the truth table, first off, how many rows of the truth table are there?
2 to the n.
Yeah.
So for each row of the truth table, we're gonna do a small circuit gadget. What we're going to do is create a sub-circuit that lights up only when that exact input is lit up and nothing else. So the way we'll make that look like is we'll do like, if there's a 0, we'll nod it. And if there's a 1, we'll ignore it. Okay, then we just AND everything together. This is a circuit. Would you agree that this specific circuit, because of the way we've put these NOT gates, will output a 1 here, if and only if the N inputs, the 8 inputs in this case, are exactly these bits. Okay, now we do that for each row. Therefore, we have several circuits such that these wires are only going to light up if that specific row is the input. Okay? Then what we do is we make an OR gate tree, let this be an OR gate tree, and if there's a 1, we plug it in. If there's a 0, we don't plug it in. Okay? Would you agree that this circuit outputs a 1 if and only if a row with the 1 in it is the input? Okay, so we have a circuit that computes the Boolean function. Okay, what is the size of the circuit? We have 2 to the n rows. We have 2 to the n gadgets. What is the size of the gadget? It's going to be 2 to the n times the size of the gadget. Yes?
Isn't it size n times a constant?
Yeah, I mean, like, so there's n inputs here, so that's going to be like n, at most n knots, n over 2, and it's something, n, yeah, fine, it's probably n, right? That looks like O of n to me. Really? Okay, can you improve this? This is a terrible construction. This is really naive. By the way, anyone remember 2110? There's a name for this thing.
Some product.
It's some product? Okay, fine. Yeah, that is the sum product. But what I'm asking is, there's a name for a Boolean circuit that outputs a 1 if and only if the input is a specific string and nothing else. A specific sequence and nothing else.
I know what you're talking about, I don't remember what it's called.
Okay. Do you?
No, I don't know what you're...
There's a Boolean circuit primitive. So there's, in theoretical computer science, the study of Boolean circuits is different in hardware. Because they use terms that we don't really care about, such as mutex. Okay? I don't know what a mutex is. I've never learned it. I'll never, and I never will.
That's a programming term, I think. That is not circuit.
That is, a mutex is definitely Boolean.
This is from threading.
Oh. A mutex is a Boolean circuit. Mutex is conditional something, right? Yeah. Whatever. It doesn't matter.
Yeah.
Okay, yeah, that sounds right.
Yeah,
Okay.
yeah.
There's an hardware name for this thing. I forget what it is. But you put 2 to the n of those together, you get your circuit. Can you improve this? Would you conjecture this is the best you could do? Okay, give me another, actually I'll just tell you guys. In 1952, a guy named Lupinov was able to prove that you can improve this to 2 to the n over n. Okay? Can you improve that further? That's still pretty bad, honestly. It's a little better than exponential. And he kind of has a recursive construction. He saves a lot of gates that way. But not that many, to be honest. It's, in fact, only polynomially faster than the other, smaller than the other one. The answer is no, which is what we'll prove next. Claude Shannon, that guy, in, I forget, 1950-something, proved you cannot beat 2 to the n over n. Every Boolean function requires, sorry, not every Boolean function necessarily, but there are Boolean functions that require 2 to the n over n size. This is a circuit lower bound, but it's not on languages or anything, it's on Boolean functions. Most Boolean functions require the circuits of this size. Certainly there are specific Boolean functions you can imagine that have very small circuits. Give me an explicit Boolean function with an explicitly small circuit. Yes?
Like,
Not what?
not N, like not the input, or,
Let's suppose there's one output for safety, but that would actually work just fine. That would be N not gates. But suppose I wanted not a computing circuit, but a decisional circuit.
and the wires don't have to be hooked up to a gate or.
Even if we suppose they were, I claim you can still make an efficient circuit for some Boolean functions. And one could be, for example, the Boolean function that requires one of its bits to be on. That would be an OR gate tree of linear size, right? That would be pretty small. So that would be a simple circuit. It's fine, they're doing something construction. They told me they were flipping breakers. Anyway, but Shannon says that this is going to be a non-constructive argument because, in fact, we don't have explicit functions that we know require large size, but we know that most of them require large size. Kind of a strange result to interpret that. The way we'll do this argument is we will simply compute a ratio of two numbers. And we'll take the limit of circuits of size 2 to the n over n, and we'll compute that ratio as the number of Boolean functions. So first off, we want to do a little bit of combinatorics and find out the number of circuits of size 2 to the n over n. So in fact, let's consider just without considering 2 to the n over n, consider n input T gate circuits. Okay, there's T gates and there's n inputs. How many such circuits are there? Well, what does a gate look like? Looks like that. Okay. How many choices are there for the circuit? Excuse me, the gate. This gate could be what? And or not. Let's just say B. Okay, for any specific circuit basis. Sometimes in theoretical computer science they consider the 16 gates, all possible two-input Boolean functions. That's the circuit basis. Whatever. Okay, so there's B possible choices for the gate. How many choices are there for the first wire?
0 or 1.
As a value, but it can connect. In some sense, we're trying to count graphs. It can connect to gates or inputs, right? So how many possible gates or inputs could it connect to?
2 inputs and B gates.
Well, B here is going to be the size of the circuit basis. There are still T gates and N inputs. Sorry, maybe my notation's not too good. Yeah?
So is it N plus T?
N plus T? Almost. You're off by 1. I claim this has N plus T minus 1 choices. This has N plus T minus 1 as well. Why was it N plus T minus 1 and not N plus T? Yeah, you don't want a gate to contain it. You can't wire the gate to it. You don't want to do that. It's directed asynchronous. Okay, fine. So we know that there are B to the T choices for labeling the gates, and we know that you can assign input wires to each of the gates. You can organize them in the fashion of N plus T minus 1 to the T, right? Sorry, 2T. Right? There's that many choices for the labeling of the gate. There are this many choices for the first input wire and this many choices for the second input wire. We've overcounted, though. We kind of assume, when we count this way, we're kind of assuming the gates are organized in a linear fashion. And we say the first gate has these choices, the second gate has these choices, third gate has these choices. That's not good. So we need to divide by something to count correctly. How many ways could we have ordered T gates?
T factorial?
Yeah. So we're going to undercount that by T factorial. Okay? Pop quiz. What is Stirling's approximation?
T over E To the T.
You're missing an unimportant term there, but that's the most important part. It's not constant, but there is a missing term. Anyone remember this? Square root of 2 pi t. No one will remember that, okay? This was done before big O, but basically big O of t factorial is that, of the constants, okay? So let's just substitute that in. This is approximately b to the t, n plus t minus 1 to the 2t, over, and then like let's reciprocal it, so this is gonna be e to the t to the t, square root of 2 pi t, okay? What is the relationship between n and t? N is inputs, t is gates. What do you know must be true about the n inputs?
Only 2 inputs per.
Yeah, so, well, there is certainly such a relationship between the way you wire the inputs to the gates, right? You can wire 2 inputs per gate. So you know something about the number of gates versus the number of inputs. The number of gates must in fact exceed the number of inputs, right? You must have more gates than inputs. So we know that n minus 1 is less than or equal to t. We can substitute, there's an n minus 1 and there's a t here. We can overestimate this by b to the t, 2t to the 2t, e to the t, over t to the t, 2 pi t, square root of 2 pi t, okay? Do we agree with that overestimation? Yes.
Wouldn't you have more inputs than gates, or?
You should have more gates than inputs because you need at least one-ish gate per input. Otherwise, you have hang-in inputs, right?
Okay.
So like, think of it like this. Let's say you had 8 inputs and 3 gates. That's like, what do those wires do now? So you want at least the first layer to contain the n inputs, right? Actually, this is a good point, and let me take a pause from the proof. Circuit complexity is strange in the sense that the size of the program is bigger than the input. That's not natural. For example, Google, big, right? Lots of data. Suppose Google was a circuit. Google takes as input the entire internet. So the algorithm that processes the internet should be as big as the internet. Not a very good model, right? But it is the one that works here. So kind of a strange analogy. Anyway, you must have more gates than inputs, okay? Do we agree with the math though? Like I've not made any algebra mistakes. Okay. We have a t to the t here and a t to the t there. If I were to get rid of that, would you agree that that's b to the t, 4 to the t, t to the t, e to the t, over square root of 2 pi t. Did I do that right?
Yeah, that's correct.
That sounds right. Okay, fine. T's abound. B, 4bet to the t over square root of 2 pi t, okay? That 2 pi t thing is just making things smaller. Let's ignore it. We overestimate by some constant c to the t. Okay? That's some constant, that's making it smaller. We may overestimate and say that the number of circuits of size t is less than or equal to some constant c times the number of gates to the power of the gates. Okay, fine. Let's plug it in. How many circuits are of size 2 to the n over n? Well, we know that's going to be some constant c, I should write it over here, some constant c times 2 to the n over n to the 2 to the n over n, okay? Let's first find this numerator here, the number of circuits of size 2 to the n. If we expand this, we're going to get c over n, 2 to the n over n, times 2 to the n over n, okay? How can I simplify 2 to the n to the power of 2 to the n over n?
To the n?
Yeah. So this is going to be c over n to the 2 to the n over n to the 2 to the n. Okay?
That's the number of circuits of size, was in fact less than or equal to that, right? Of size to the n over n, okay? How many Boolean functions are there of n inputs?
B to the T.
So we're not asking about circuits. The number, just consider, we're trying to compute a ratio of circuits to functions, and we're trying to hope to show that there aren't enough, in a Kolmogorov sense in fact, there are not enough circuits for the amount of functions we have. How many Boolean functions are there? We did it earlier, right? Yeah. So the number of circuits of size n is, just to be clear, this ratio of circuits of size 2 to the n over n over the number of Boolean functions is C over n, 2 to the n over n, 2 to the n, and the number of Boolean functions is 2 to the n, okay? So what is C over n, 2 to the n over n? If you take the limit of n gets big enough, what is the ratio, what is this equal to? It's a pre-calc question.
0?
Yeah. This gets much bigger than that gets bigger, right? So, in fact, what we can say is as we take this ratio, the limit of n gets big enough, there are simply not enough circuits than there are functions. There are way too many functions, and there are not enough circuits. Even with a very generous overestimate on the number of circuits, there's still not enough circuits. There's way too many functions and not enough circuits. Therefore, most circuits must exceed size 2 to the n over n. But Lupinov proved that every Boolean function has a circuit of this size. Therefore, we know most Boolean functions must have circuits of this size. Very few of them do not have circuits smaller than this, right? Very trivial circuits have, very, very trivial functions, very few of them have circuits smaller than this. Most of them require circuits of that size, and so in some sense, it's optimal. Such a brute force construction is the best you can hope for. That said, so we know most Boolean functions have exponential size circuits. That's great. All we need to do to prove P does not equal NP is prove that SAT has exponential size circuits. We just proved most of them have exponential size circuits. Can we do that? No, okay, well, so here's the first problem. We just proved most Boolean functions require exponential size circuits. We need to now just prove an explicit function an explicit function has exponential size circuits because we proved most of them do. So obviously we should be able to find one. 1986, they were able to prove a problem in NP has a circuit lower bound of 3n minus little o of n, okay? That's barely above linear. That's actually, in fact, not above linear. That's something terrible, okay? But this is a problem in NP that was shown to have almost a linear circuit lower bound. Not that good. This stood for like generations until 2016, and I think 2022 was also improved. They were able to improve this result to, you're not going to believe this, 3 plus 1/86 n minus little o of n. For a specific kind of problem in NP, it's called a fine dispersors. Doesn't really matter. But people were looking at explicit functions that were like, yeah, this one has to be hard to try to prove a circuit lower bound. For example, sum of products of sum of products, right? Certainly that's got to have enough alternating stuff going around there that is probably big. Fine dispersors is such a problem where it's just like, the definition of the problem involves a lot of switching. So it's like, it better have a lot of circuits to do so. You can't really, I mean, that's not a very good lower bound though. I mean, it is the best we can do though for explicit problems. This is a very simple problem with a very small lower bound. We are asking to prove a very hard problem has a very hard lower bound. We are, at least so far as we've seen, we are very far from proving something like this. Right? Are there any questions on this? I'm going to give you an actual circuit lower bound in a second on such a simple problem. But are there any questions on this? Okay. So people looked in the first, they took some of the stuff from really, I guess, cybernetics, because they were looking at networks and circuit complexity kind of stuff, without calling it that. In a non-combinatorial way, and they were looking at very simple problems to prove had circuit lower bounds, right? One such problem we'll just do as a warm-up is the threshold function. Threshold of k and n is outputs 1 if greater than or equal to k of its n inputs are 1. So threshold is, in some sense, is one of these simple functions, okay? Simple functions are, in fact, the threshold function. Another one is the parity function. You have to, the XOR of n bits. Another one is the majority function, right? So is a majority of the bits on? Is a certain threshold of the bits on? Is the XOR of the bits on? Such simple problems, maybe we can show lower bounds on. In fact, we can. So such simple problems are what people first explored. Before we went to SAT, and looked at SAT, we looked at problems like this, right? Would you agree that these are probably simple? Fine. We can prove that threshold of 2 to the n requires circuits of size 2 to the n minus 4. First off, not a very good lower bound. It's linear, and it is not a big O either. It's just literally a 2 in the n minus 4. Here's kind of the core idea in the proof. We can prove so by induction, because if you take a threshold function, if you take threshold of 2 to the n and cut parts off, you can end up with a threshold of 2 to the n minus 1 circuit, which you can then apply an induction hypothesis to and build back up, right? So in fact, all these functions kind of naturally contain within them subcircuits that solve the same problem on smaller inputs, right? The parity function, as we showed, contains subcircuits for the parity function on 2 bits, right? And so on. Are there any questions on what we're proving before we do so? Okay, base case. Inductively, n is equal to what? What's the smallest base case that makes sense? But if you plug in 2, you have a circuit of 0 gates, which I think the books are like okay with that, but I don't understand how that works. So let's not think about that one. Let's try 3. I mean, I think that some convention could figure that out. I'm not gonna worry about that. Give me a threshold function on 3 gates. Let's say we have 3 inputs. Give me a Boolean circuit, and let's suppose our basis B is all 16 2-input Boolean functions. Okay. The basis actually matters, especially when you're doing constant size stuff like this. But give me a Boolean function, give me the Boolean circuit with a certain number of gates that does this. And let's just do and, ors, and nots for simplicity. This is a good exercise. Again, I want a Boolean circuit with 1 output and 3 inputs that outputs a 1 if 2 of its inputs are on. Any 2 of its inputs. Then you don't need to give me a small circuit either. Just give me any circuit.
Exactly 2?
No, it could be all 3.
Could be all 3, okay.
We already said the word for this actually today in class. I don't know if you remember. Sum of products. Does that help? What's the circuit?
And exclusive OR.
That would also probably work. I just don't know how to do it. I'm just going to do the only one I remember. Okay. Okay? But why does it require circuits of size n? If we plug in 3 here, what do we get?
2.
Yeah. Why does it require at least 2 gates?
Because you need at least 3 input wires,
Sure.
which needs at least 1.5 gates.
Yeah, I like that. The way I could say that is I could say, since all 1-gate circuits are wrong. Any 1-gate circuit will not decide the majority function on 3 inputs, even if you have literally all 16 possible 2-input gates, okay? The XOR, the AND, the OR, the NOTs, whatever. You have every possible combination. Doesn't matter. They're all wrong. Every single one of those will not do majority of 3 inputs. Fine. So now assume our induction hypothesis. Assume that the threshold of n-1 of 2 requires two n-1 plus -4 gates. Consider a circuit for threshold n of 2. And let this circuit be denoted like this. Okay. We have n such inputs. There is some last gate, would you agree? So let this last gate be G. And let G be connected to 2 other inputs, let's just say. Let's suppose it's connected to Xi and Xj. Okay? This is some gate G. It's connected to Xi and Xj. Let me just erase that so we can clear picture works, okay? I claim, here's a lemma. Xi or Xj are connected to some other gate. Okay, I claim that either Xi or Xj or both are wired up to some other gate. There is some G prime that exists here, okay? Xi is somehow plugged into there. Proof, assume to the contrary, Xi, Xj are both connected only to G, okay? Hard code Xi and Xj. If they're only connected there, we have these inputs that are not really important. Xi or Xj could be one of the following: 0, 0, 0, 1, 1, 0, 1, 1, okay? If we fix Xi and Xj to be 0 and 0, this is still a circuit, C, that computes something. What does it compute? What Boolean function is computed if we fix 2 inputs to be 0? This is kind of an inductive step. I claim it computes a threshold function of what?
n-2.
2 n-2, yes. Okay. What if one of them is 1?
2 n-1.
1 n-1, yes, 1 n-1, because one of them's already on. So we need threshold of 2, we need at least one more to be on, and it's n-2. Okay, yes. Okay, and what if both of them are on? I guess it's technically threshold of 0 of n-2, right? So if you fix the output, if you fix the inputs to G prime, you can compute this circuit, whatever that fixing is, could be one of 3 possible Boolean functions. This circuit C prime computes one of three possible Boolean functions. Would you agree, you can either, if it's the case that xi and xj are wired up only to g, that you can fix xi and xj, or equivalently, fix the output of g. Okay? So, replace C, just delete G. So, C minus G is some circuit without that gate G, okay? Remove this circuit, and whatever its output wire is hard-coded to be fixed. What is that circuit, though? I don't know, but I know one thing. Is two possible circuits. To compute three possible Boolean functions. This is impossible. Contradiction. So, suppose xi is connected to some other gate G prime. Okay. So let's be clear on what happened contradiction-wise. You can either fix this output wire here and get two possible circuits. C minus G could be two possible circuits. One with a 0 hard-coded there, one with a 1. Either way, it's only two options. But those two options somehow have to equivalently compute three possible Boolean functions. Two possible circuits must be three possible functions. And it's not the case that you can eliminate a function either. It must be one of these three. These two must be one of these three. That's impossible. These two could be one of these two, or these three could be one of these three. These don't match. So obviously there's a contradiction. So we may assume that both xi and xj are not connected only to this gate G. One of them's got to be wired somewhere else. So let's just suppose xi is connected to some gate G prime. We can assume that now by our lemma. Questions so far on just this lemma we've proven? Okay. What does C minus G prime compute? Let's take a second on that. This is part of the core of the proof, so I want to massage it for a second. I guess what I'm asking is, what Boolean function is computed by this? I'll even go farther. I claim it's a threshold function for what inputs, what outputs. Well, we're removing the wires, we've removed the gates that xi is wired up to. So it's in some sense we've really removed xi. So we had previously n inputs, and now we have n minus 1 inputs, right? But again, we don't know anything about xi here. So we still need threshold of 2. So this is still 2. Yes?
Assuming xj could be connected to a different gate, or is it only connected?
So we assumed that in the proof by contradiction that both xi and xj are connected to g. So when you do the opposite of that, one of xi or xj or both are connected to something else.
So we remove g and g prime, we're effectively removing xi and xj from the inputs?
Without loss of generality, suppose that xi is connected to g prime. It could have been xj or both, but one of them is connected somewhere else. So just suppose it's the one we call I. Could be, you could swap the labeling, right? So just whatever that one's connected to, delete both those gates. I claim that's going to compute the threshold function of n minus 1 on size 2. N minus 1 inputs, it needs two outputs to be on. Okay. What do you know about a circuit that computes the Boolean function of threshold of n minus 1 inputs of 2 must be on? 2 of n minus 1.
It requires that one, yeah. 2 times n minus 1 is 4.
by the induction hypothesis, this circuit must exceed 2 to the n minus 1 minus 4. Right? Any circuit that computes that function must exceed this size. Right? But we're not looking for in terms of C minus G prime. We're looking what the size of C is. Because C is what's going to compute threshold of n. 2 of n. Where'd it go? Where'd it go? Yeah, threshold of 2 of n, right? So what is the size of C then? C minus G prime is C if you took out 2 gates. Add those 2 gates back in. Okay? This is a technique called gate elimination. Okay? It's not a very advanced technique. It's a very simple technique relative to the rest of the stuff that is done. You take the circuit, you chop it up a little bit, you find a smaller circuit in there. Apply the induction hypothesis, you get a circuit lower bound by induction, basically for free. Then you do a little bit of arithmetic and then it propagates forward. Okay? This is basically every gate elimination technique works this way. Right. Questions on this? It's not particularly important you understand the proof, but I wanted to show you a simple, explicit circuit lower bound that we have. Yes?
And so this proves that you need 2 to the n minus 4 circuits for th 2 to the n?
Yeah, if you wanted to compute the Boolean function, 2 of n, where 2 of the inputs, at least 2 of the inputs must be on of the n, and you assume that you have a basis of all 16 possible gates, you must have 2 to the n minus 4 gates in your circuit. If you were to actually figure it out, that would probably be, you would probably, I don't know if that's optimal, but that's like, that sounds reasonable. That's not even a very good lower bound if you think about it. It's a linear lower bound, which is almost, I mean, we basically said that at the beginning, right? So, yeah. Question on this technique? Okay, this next part is less formal, but I just want to talk to you about the history of circuit lower bounds. So, basically what happened is that people found such techniques, they found circuit complexity to be rather rich, and in the sense they can apply a lot of combinatorics that was being developed. People were coming out with new combinatorial lemmas and stuff, and immediately trying to apply them to circuits. And again, the golden goose is to show that SAT has no polynomial circuit. But what really the first result that started was that the parity function could not be computed in AC0. AC0 is a class known as, it's kind of a very simple class. It's constant depth, poly number of gates, unbounded input, okay? A bit cumbersome to work with there, but AC0 is a class of languages decidable by polynomial gate, constant depth, unbounded input circuits. Very specific class. People were able to prove that the parity function was not an AC0, and this was a monumental result. In fact, first Sachs and Sipser, you guys heard of Merrick First? Merrick First is wandering around the department somewhere. He was the one who proved this in 1981. So he invented this very complicated technique to do so, which is basically like, first off, the parity function is a very simple function. And in fact, it's a highly sensitive function because a simple change, as you change a single bit of the input, the whole output changes. It's very, very sensitive, right? So what you do is you assign a probability distribution to the inputs. And you say, the method of random restriction. It's like, if we were to restrict the input, like hide parts of the input, how does that change what the probability output will be? It's called the method of random restriction. And through, if you're familiar with the probabilistic method, it kind of follows these techniques. It's very advanced. People were able to show such lower bounds like this, bringing in math from very, very, very different areas. In fact, basically, Sipser has like a retrospective on how he was able to prove this. He said he looked to descriptive set theory. He first proved it in the infinite case. Consider the infinite parity function on infinitely many wires. And then used techniques and things from like analytic set theory and Lebesgue measurable sets and all kinds of really advanced set theory stuff to show in the infinite case. And then he was able to simplify that proof to the finite case. So he went to logic and set theory. Another guy was able to prove this by going to model theory and some other things. So this was one of the first results proven. And it went through a lot of advanced math that had to be brought into combinatorics just to show this.
By the way, kind of a terrible result if you think about it. This is a really stupid class. It's not very, like, P is a good definition of polynomial time. It's like good. It's like that's efficient. Would you conjecture that AC0 is like a good definition of efficient circuit? Constant depth is kind of useless. It's kind of too small, in fact. You know how we say that every algorithm should take at least linear time because it takes that long to read the input? That's kind of like, that's at least a linear time lower bound. I'm claiming here a constant depth lower bound. That's even worse, right? That's terrible. And the parity function is one of the worst problems to be put in there because it's highly sensitive. It's the most sensitive function, in fact, by definition. So it is the circuit that definitely should not take constant depth to compute. But proving this is a very difficult problem. People refine the proof over generations. In fact, one of the best proofs to some was basically like AC0 can be approximated by low degree polynomials. And then you prove that parity cannot be. And that's enough to show that parity is not an AC0. So there are some proofs that have been simplified in such a way that would literally take us one full lecture, but it would be very difficult. It'd be like Fourier series and stuff involved. But such things are not impossible. So basically from 1981, where first Sachs and Sipser invented this method of the random restriction, did people try to prove the golden goose? Again, SAT does not have a polynomial size circuit. Or perhaps even prove SAT is not constant depth, you know? And this was a generation in history that people got really good at proving circuit lower bounds on restricted functions. Specifically, the majority function, the parity function, the majority function, the threshold function. There's also something called a Sipser function, which is ands, abors of ands, or something like this, right? So there's a few other simple functions that people got good at. But people felt pretty far away from proving SAT. SAT is nothing like these problems. SAT is a very difficult problem, right? It's the search problem, really, in some sense. So why were we unable to prove that? And these two guys in 1995, so this was like 1981, this started, people got good at it, and around 1995 these guys came out with this result. Razborov and Rudich said, all of these proofs are what they would call natural. So here's the way a natural proof looks. First, make up a measure, such as some are discrepancy, sensitivity, scatter. Just make up something like that, okay? Prove P/poly is low in whatever measure it is. Prove SAT is high. Okay? Under certain conditions, no technique can prove this. If you can prove that P/poly is like low, it's like simple, they have low scatter, whatever that means, and then you prove SAT is high, it's complex, it can't, that's enough for you to conclude these two can give you that SAT is not in P/poly. What Razborov and Rudich do is claim that they call this class of techniques natural proofs. A proof is said to be natural if it follows this very similar pattern. There is some kind of circuit description, there is some kind of measure description of the class. Then there is a measure of the Boolean function, and then a claim that the Boolean function is high in the measure while the class is low. No such proof that is natural can solve P versus NP. And just to give you a detail of how they do it, in cryptography, we know very well about the relationships between the hardness problems and open complexity questions. So it is known, for example, P does not equal NP if and only if pseudo-random number generators exist. A pseudo-random number generator is said to be strong if there is no polynomial time algorithm that can tell it apart. So in the sense, like, let's suppose you give an algorithm, a polytime algorithm, randomness, true randomness, and pseudo-randomness, okay? And if it can say, through some majority of the time, it's not even like overwhelmingly, just enough, That's random and that's pseudo-random. It can tell them apart. That only can be done if P equals NP. So if P does not equal NP, pseudo-random number generators exist. So, I mean, we use pseudo-random number generators all the time. This is good evidence that, by the way, we also know this is true if and only if hash functions exist, right? So here's the outline of their proof is basically like assume sat is not in P/poly, has a natural proof, use this proof as an algorithm to distinguish randomness. And if you can distinguish randomness, that implies that P equals NP. But we know that if sat is not in P/poly, then P is not equal NP. This is a barrier. It's called the natural proofs barrier, and it's very similar to the relativization barrier, except it's combinatorial, one-sided, and much more difficult. I'm not even going to be able to get into a single proof that naturalizes because it would take us over an hour, right? But just trust me that there's a lot of combinatorics in the way that those proofs exist. So it doesn't say anything about a natural proof that might show P equals NP, but that's of course not believed at all. So basically what happened is a generation of scientists got really good at this technique. They advanced, they published thousands of papers on this result. Rasborough and Ruters come around and say, okay, it's not gonna work, guys. Go home. This whole era in history, 15, 17 years, it's over, right? And again, I'll give you the history of the P versus NP problem. Let this axis be the confidence we have in solving the problem, and let this be a function of time. Cook defines the problem in 1971. He says it'll probably be solved quickly, right? And then people play around, they discover Savage's theorem, Leibniz's theorem, basic elementary results come out, time hierarchy theorems and so on, right? And then the relativization barrier comes out and it's over, because all the techniques that we know how to do, none of them are gonna work. So like, okay, this is 1975, we need to find new techniques. There's a short period that people are convinced that P versus NP problem might be something like undecidable. But this is very quickly abandoned after like 2 papers. Then circuit complexity stuff comes out, right? People are like, wow, we can prove parity is not an AC0. We have an explicit lower bound on an explicit function, unconditionally so, right? Maybe we can just generalize this technique very strongly to prove P does not equal NP by proving sat is no polynomial circuit. That was the conjecture at the time. And in fact, there was some moderate success. In fact, Rasborough was able to prove clique has a monotone circuit of size, or not just has, requires monotone circuits of size super polynomial, right? Whatever it is. Something bigger than polynomial, I forget exactly. It's not exponential, but it's like 2 to the log or something, right? It's big. And people get really hopeful about that because like, wow, a monotone circuit, by the way, is one that does not have NOT gates. It's actually trivial to satisfy a monotone circuit because just make all the inputs 1. So it's not very interesting. And he's able to prove that a special kind of restricted circuit, if it solves an NP-complete problem, it has to be a big circuit. And people are fanatic about this. And then the next paper is like, okay, if you add NOT gates, the technique doesn't work anymore. So it's a little bit of over. But people are still convinced that these circuit techniques are gonna work. So there's still a hope. People are investing themselves in the technique, and then the natural proof barrier comes and it's over, okay? So a generation of scientists invented this class of techniques simply because of the relativization barrier. So a failure, again, history of complexity theory is a history of failure. The failure of proofs that relativize inspired a generation of people to work on something else. Combinatorics, problems, circuits. The fact that those didn't work now inspired the next generation. People tried stuff with polynomials, and then there was a barrier to that. And then there's little techniques. There's like 2 papers that I know of that don't fall into one of these general classes. There's relativization barrier, there's the natural proofs barrier, there's algebrization, there's other little tiny things that don't really matter. For example, restricted barriers exist all the time. But we have all kinds of results that say, this is not gonna work. Like, we gotta try something else. So it seems easier to prove that someone else can't prove the problem than it is to prove it. Question?
Where do you say we are now on the confidence?
Oh, there's no hope. I mean, it's totally gone. I mean, because And this is the reason why you shouldn't believe people on the internet who try to solve P versus NP, because they don't understand the prior work that has been done, right? When you skim a paper, there's a guy who keeps commenting on my YouTube, please check out this paper. He proves through, a linear program that he found a polynomial time algorithm for an NP-complete problem. But by skimming the paper, I know it relativizes immediately. I don't have to read any further. It falls into this category. So without reading further, I know it's wrong, you know? He didn't bother to learn anything before trying to solve an NP-complete problem in polynomial time. He just is convinced his algorithm works. So he's not gonna listen to anybody, he's just gonna do his own thing. Why was I talking about this? Yes, we know that there are basically no techniques that do not fall into these three loose categories. So if there is a proof of P versus NP, it has to be so creative, so new, and so different that that will also be a contribution. So like, we know what a proof will look like if we will see it. Maybe the opposite, maybe we don't know what it'll look like explicitly. We don't have the tools yet to solve the problem, if we can even do so. But we know that, we know what it doesn't look like. We know what the proof doesn't look like. We don't know what it does look like, right? One more thing I'll mention is that Razvarov conjectures after the natural proofs barrier, like, many arguments of this form can be formalized in a kind of bounded arithmetic. In the sense that all these proofs kind of seem to follow from the same weak set of axioms. So and this work was extended over by other scientists, and we got something like, I think, did I talk about PV before in class? I think so. I'll just say it again. PV, let this be a set of axioms which attempts to encapsulate simple proofs. This was defined by Cook, it's an equational theory. Basically, like, a proof is simple if it can be proven from PV, okay? This theory is so weak, this set of axioms cannot prove the pigeonhole principle, for example. That proof is too long. In 2016, some people were able to prove that PV cannot prove P equals NP. So either P does not equal NP, or a proof that P equals NP is very long. I won't just say what that means in a formal sense. But we have kind of like mini independence results, right? It's easier to prove someone can't prove something than it appears to be. You can't prove anything, but you can go around this in two ways. Either you prove conditional results, assume P does not equal NP, these things must be true. That's fair game. Or you prove other people can't prove things, which is also less successful, but moderately so, right? The field of complexity theory, no one's solving any problems. No results are unconditional. I mean, there's a few, I'm sure, but like this kind of stuff. It's all kind of like, I don't know, it's got a feeling of hopelessness that I don't think any other branch of mathematics has. So, questions? All right.